Hi, hello. Welcome back to Max Tuni. In this video, I am going to discuss the problem 20.8, and these are related to residues. In my last video, I already discussed the topic residue and how to calculate residue at poles, if it is simple or a pole of order n. And the first question, we are asked to find residue using the Lorentz series. I already discussed how to find residue using Lorentz series expansion of f of z in my last video, concept of residues. And in this video, I am going to solve 2, 3 and 4th question. So let's start. Second question is, find the residue of z e raised to z divided by z minus 1 all cube at its pole. F of z is given by z e raised to z divided by z minus 1 whole cube. And clearly z equal to 1 is a singularity and it is a pole of order 3. Z equal to 1 is a pole of order 3. We already discussed the topic how to find residue at a pole of order n. That is residue of f of z at z equal to 1 is given by 1 by n minus 1 factorial. That means 3 minus 1 factorial, 2 factorial into limit z tends to 1 d 3 minus 1 d square divided by d z square z d raised to z. Z square z minus 1 all cube into f of z, that is z d raised to z, and it is equal to 1 by 2 limit z tends to 1. Differentiate with respect to z. First derivative is d by dz is z into derivative of e raised to z is e raised to z plus e raised to z into derivative of z is 1. And second derivative, first is z, e raised to z is e raised to z plus e raised to z into 1 and plus derivative of e raised to z is e raised to z. This is z e raised to z plus 2 e raised to z. Now limit z tends to 1, z e raised to z plus 2 e raised to z. Now putting the limit, we get 3 e raised to 1. Z equal to 1, e plus 2e means 3. That is 3e by 2 is the answer. Question, z square divided by z square plus a square at z equal to ai. We can write it as z square divided by z plus ai into z minus ai. That is z square plus a square. Now z equal to ai is a simple pole. Z equal to ai is a simple pole. We know that residue at a simple pole, residue of f of z at the simple point z equal to ai is given by limit z tends to ai, z minus ai into f of z, which is equal to limit z tends to ai, z minus ai into f of z is z square divided by z plus ai. Now putting the limit z equal to ai. ai all square is a square, I square is minus 1 and ai plus ai is 2ai. This is minus a divided by 2i and 1 by I is minus I and minus minus plus. So ai by 2 is the residue. Next question. Determine the poles of the following functions and the residue at each pole. So first find poles of these three functions and find residue at poles. First function is f of z is equal to z square plus 1 divided by z square minus 2z. First find the poles of this function. So we can write it as z into z minus 2. Clearly we have two poles, z equal to 0 and z equal to 2 are poles and which are simple poles. Simple poles. In order to find the order of poles, you should consider the denominator and 0. What is the order of 0 of the denominator function? If z equal to 0 is a simple 0 of this function, then it is simple pole of f of z. And note that z equal to 0 is not a 0 of numerator. Okay. So z equal to 0 and 2 are simple poles. Now let's find the residue at z equal to 0 of f of z. Residue at a simple pole. So we can write limit z tends to 0, z minus 0 into f of z. That means limit z tends to 0, z square plus 1 divided by z minus 2. Putting the limit, we get 1 by minus 2. That is minus 1 by 2. Now residue at z equal to 2 of f of z is limit z tends to 2, z minus 2 into f of z, which is equal to limit z tends to 2, z minus 2 into f of z, that is z square plus 1 divided by z. Now putting the limit, we get 2 square plus 1, that is 5 by 2. These are residues at these poles, simple poles. Now second question, f of z is equal to z square minus 2z divided by z square plus 1 into z plus 1 whole square. Find the poles. Consider the denominator. Z square plus 1 is 0 when z is equal to plus or minus I, and z plus 1 whole square, z is equal to minus 1 is a pole, and z equal to minus 1 is pole of order 2, and these are simple poles. Now let's find the residue at z equal to I f of z. Z equal to I is simple pole. We can write it as limit z tends to I, z minus I into f of z. We can write this function as z square minus 2z divided by z plus I into z minus I into z plus 1 whole square. Z square plus 1 is z plus I into z minus I. So z minus I into f of z is limit z tends to I, z square minus 2z divided by z plus I into z plus 1 whole square. Taking the limit, z tends to I square minus 2I divided by I plus I 2I into I plus 1 whole square and plus I whole square. I square is minus 1 minus 2I into 1 plus I whole square is 2I. So this is minus 1 minus 2I divided by 4 into I square is minus 1. So minus 1 cancel with the numerator, 1 plus 2I divided by 4 is the answer. Now residue at z equal to minus I f of z is limit z tends to minus I, z minus minus I, that is z plus I into f of z. So that is limit z tends to minus I, z plus I into f of z is z square minus 2z divided by z minus I into z plus 1 whole square. Taking the limit z equal to minus I square is minus 1, I square that is minus 1, minus 2 into minus I means plus 2I divided by minus I is minus 2I into minus I plus 1 whole square. Minus 1 plus 2I divided by minus 2I into 1 minus I all square is minus 2I. This is a plus b whole square and a minus b whole square. This is 2I and this is minus 2I. So what we get minus 1 plus 2I divided by 4I square minus 1 and minus 4. So what we get 1 minus 2I divided by 4 is the answer. Now next, residue at pole of order 2 z equal to minus 1. Let's calculate it here. For residue at z equal to minus 1 of f of z. Minus 1 is pole of order 2. We have the formula 1 by 2 minus 1 factorial, that is 1 by 1 factorial into limit z tends to minus 1 d 2 minus 1. That means derivative d by dz of z minus I, that is minus 1, that is z plus 1 all square into f of z. So limit z tends to minus 1 d by dz of z plus 1 all square into f of z is z square minus 2z by z square plus 1 divided by z square plus 1. I am writing z square plus 1 instead of z plus I into z minus I. Now find the derivative z square minus 2z divided by z square plus 1. Just erase this. Okay. Now differentiating limit z tends to minus 1. Differentiating this is u by v form. So denominator into derivative of numerator, that is 2z minus 2 minus numerator z square minus 2z into derivative of denominator 2z divided by denominator square. No need to simplify this formula. Now let's put the limit z equal to minus 1. This is minus 1 all square, that is 1 plus 1, 2 into 2 into minus 1, minus 2, that is minus 4 minus 1 all square, 1, 2 into minus 1 is 2, minus 2 and this is minus plus 2. So 1 plus 2, this is 3 into 2 into minus 1 is minus 2 divided by 1 plus 1, 2 square 4. So we get minus 8 plus 6 divided by 4, that is minus 2 by 4. It's minus 1 by 2. Fourth question is 1 minus e raised to 2z divided by z raised to 4. Z equal to 0 is pole. Find residue of f of z is z equal to 0 using series expansion, since here e raised to 2z is there. So e raised to 2z, series expansion of e raised to 2z is 1 plus 2z plus 2z all square divided by 2 factorial plus 2z all cube divided by 3 factorial plus etc. And 1 minus e raised to 2z is 2z minus 2z minus 2z all square divided by 2 factorial minus 2z all cube divided by 3 factorial minus etc. Now 1 minus e raised to 2z divided by z raised to 4 is minus 2 divided by z cube, z cancel, and minus this is 4z square by 2 factorial into z raised to 4 minus this is 8z cube by 3 factorial into z raised to 4 etc. And here we get minus 2 by z cube minus 2 divided by z square minus 8 by 6 z minus etc. So residue of f of z at z equal to 0 is the coefficient of 1 by z, that means a minus 1. Here coefficient of 1 by z is minus 8 by 6, that means minus 4 by 3. Minus 4 by 3 is the residue of f of z at z equal to 0. F of z is equal to z raised to iz divided by z square plus 1. Here z equal to plus or minus I are poles. Z square plus 1 equal to 0 when z is equal to plus or minus I. And these are simple poles. So we can calculate residue. Residue at z equal to I, f of z equal to limit z tends to I, z minus I into f of z. And this is, we can write z raised to iz divided by z plus I into z minus I. So this is limit z tends to I, z raised to iz divided by z plus I. I e raised to I into I is minus 1 divided by I plus I is 2i. Means a raised to minus 1 divided by 2. Now residue at z equal to minus I f of z is limit z tends to minus I z plus I into f of z. And z plus I into f of z is limit z tends to minus I z plus I into minus I z plus I into f of z is z raised to iz divided by z minus I. When putting minus I, we get minus I e raised to minus I into I is plus 1. I square minus 1 and already there is a minus. So this is plus 1 divided by minus I is minus 2i. So I cancel. This is minus e by 2. Sorry, minus 1 cancel. This is e by 2. Question f of z is equal to cot z. Cot z means cos z divided by sin z. So singularities of f are zeros of sin z. Sin z equal to 0 when z is equal to n pi for n belongs to integer z. So residue f of z at z equal to n pi. This is equal to n pi means z is equal to 0, pi, 2 pi, 3 pi and minus pi, minus 2 pi. These are the poles and these are simple poles. These are simple poles. Instead of finding residue at z equal to 0, z equal to pi separately, we can use residue of f of z at z equal to n pi generally. So this is limit z tends to n pi z minus n pi into f of z. Instead of finding this, or we can use this formula, we can use this is z equal to n pi are simple poles and this is of the form p of z divided by q of z. Then residue is if it is a rational function p of z divided by q of z. Numerator is a function of z and denominator is a function of z, and p and q are analytic at z equal to n pi. Cos is analytic, cos z and sin z are separately analytic functions. So we can use the formula residue at z equal to n pi is, if it is in the form p of z by q of z and z is equal to n pi are symbol poles, that means f of z as symbol pole, we can use the formula p of, if z equal to a is the singularity, then p of a divided by q dash of a is the residue. So here we can use this formula. Now p of a, that means cos n pi divided by derivative of sin z, that is cos z, and putting the term z equal to n pi, this is cos n pi, that means 1. 1 is the residue. Or we can calculate using this. Residue is limit z tends to n pi, z minus n pi into f of z. That means limit z tends to n pi, z minus n pi into cos z by sin z. Now putting z equal to n pi, we get 0 divided by 0. This is 0 by 0 form. So use elasible rule, means differentiate numerator and the denominator. So z minus n pi into derivative of cos z is minus sin z plus cos z into derivative of z minus n pi is 1 divided by derivative of sin z is cos z. Now put z equal to n pi. This term will 0 and this is cos n pi divided by cos n pi. We get 1 as residue. So residue of cot z at z equal to n pi at 1. Hence we solved all the questions in 4th also. We solved 2, 3, 4. Next video we solve 5, 6 and 7 using the residue theorem.